Imagine for a second that you want to learn a brand new language. Let's say, I don't know, Finnish.
Okay, finish?
Yeah, but the only way you're allowed to learn it is by taking multiple choice tests.
We just taking tests.
Just tests. You don't get a textbook, you don't have a teacher explaining the grammar rules to you, and you are definitely not allowed to just sit down and read a Finnish novel.
That sounds like a complete nightmare.
Right, you just get a sheet of paper, you guess an answer, and someone yells wrong or right at you over and over again.
I mean, you'd eventually memorize a few answers, sure, but you wouldn't actually know Finnish. You'd just be a test-taking machine with zero context.
Exactly. And yet, for a surprisingly long time, that is precisely how we were trying to teach artificial intelligence to understand the world.
Yeah, the supervised learning trap.
Right. We were stuck in this massive bottleneck. Because if you think about it, we have oceans of text out there. The entire internet, digital archives, libraries.
But almost none of it is graded homework.
Exactly. It's all unlabeled. And until recently, deep learning models were just incredibly needy. They demanded labeled data.
They needed the answers in the back of the book or they couldn't learn a single thing.
Which is a huge structural problem for the field of NLP, natural language processing.
It really is, because labeled data is incredibly expensive. You need humans to sit there and manually tag sentences as happy or sad or true or false.
Yeah, you can't just crowdsource the entire internet.
No, you can't. And if AI can only learn from manually annotated data sets, we are severely limiting its potential. There just aren't enough humans on Earth to label the whole world.
But then a group of researchers at OpenAI asked a completely different question. They asked, what if we let the model just, well, read?
Just read raw text.
Right. What if we let it devour books, page after page, without a teacher grading every single sentence, and only after it's read the library do we give it the specific test?
That question is really the core premise of the deep dive we're taking today.
Yeah, it's a big one.
We're looking at what might honestly be the origin story of the modern AI revolution. The paper is titled Improving Language Understanding by Generative Pre-training.
By Alec Radford, Karthik Narasimhan, Tim Solomons, and Ilya Sutskever.
Right.
So for you listening, this is essentially the birth of GPT. But before it was a household name, before it was everywhere, it was just this paper proposing a two-stage revolution.
A very elegant two-stage process.
Stage one is generative pre-training, letting the model read raw text just to learn how language works.
And stage two is discriminative fine-tuning, giving it a quick crash course on a specific task.
It sounds so simple to us now, but at the time, this was a radical shift, right?
Oh, absolutely. The mission here was to prove that a universal model, a generalist, could actually outperform systems that were hyper-specialized for single tasks.
They were trying to build a Swiss Army knife in a world full of specialized screwdrivers.
That's a great way to put it.
So let's unpack how they actually pulled this off. I want to start with that first stage, the pre-training phase. The library phase, basically.
The unsupervised pre-training.
Right. Now, unsupervised sounds a bit like, I don't know, leaving a toddler alone in a room with a box of crayons. What is the actual goal here when we say unsupervised?
The goal isn't to modify the learning objective for a specific task yet. It's really to find a good initialization point.
A starting line.
Exactly. Think of it this way. If you want to train someone to be a top-tier corporate lawyer, you don't start by teaching them specific case law on day one of kindergarten.
Hopefully not.
Right. You teach them to read first. You teach them history, logic, how arguments are structured. You give them a broad liberal arts education before they ever specialize.
So in this analogy, the model is the student and the internet is the liberal arts college.
In a sense, yeah. But here is the fascinating catch. They didn't just scrape the random internet. They used a very specific data set.
The BooksCorpus.
The BooksCorpus.
I looked into this because it's such a weird detail. It contains over 7,000 unique unpublished books.
Yep.
We're talking amateur adventure, fantasy, romance novels.
It is a very unique collection of writing.
But I have to play the skeptic here for a second. Why unpublished books? If you're OpenAI and you want to build the smartest AI in the world, why are you training it on amateur vampire novels and self-published thrillers?
It sounds counterintuitive, I know.
Why not feed it the New York Times or Wikipedia or the Encyclopedia Britannica?
Yeah.
People were using the 1B-word benchmark back then, right?
They were. But there are two really crucial reasons they went with BooksCorpus. First, it's about contiguous text.
Contiguous meaning flowing together.
Right. News articles, tweets, even encyclopedia entries, they're relatively short. They jump from topic to topic rapidly. But a novel, Even a cheesy romance novel has a long thread of consistency.
A narrative arc.
Exactly. Characters introduced on page 1 are still interacting on page 50.
So the model has to learn to remember things over a much longer period of time.
That's the key. It forces the model to learn long-range information. If you're training an AI on shuffled sentences, it never learns how a paragraph connects to the one before it.
That makes sense.
But by reading full novels, the model learns to hold a thought. It learns that if a character is holding a coffee cup in the first sentence, they probably shouldn't be typing on a keyboard with both hands in the next sentence.
Okay, I see. And what was the second reason for using unpublished books?
It's a bit more practical. They needed to avoid test contamination.
Oh, like cheating?
Basically, yes. If they trained the model on famous books, say Harry Potter or 1984, there's a very good chance that the test questions and the NLP benchmarks they use later on might actually reference those specific books.
I see.
They didn't want the AI to pass the test just because it memorized the answer key from the internet.
Oh, well.
They wanted it to pass because it fundamentally understood the English language.
So using unpublished books ensures the model has never seen the material before.
Exactly. It's like giving a student a reading comprehension test on a book they couldn't possibly have read the Cliffs Notes for.
That is incredibly smart. Okay, so we have the data. 7,000 unpublished novels. Now we need the brain. The engine reading these books.
The architecture.
Right, and this is where the transformer comes in.
Specifically, they used a 12-layer decoder-only transformer with masked self-attention.
Now we hear the word transformer all the time today, but back then the standard was something entirely different, right? Something called an LSTM.
Yes, the long short-term memory network. The LSTM was the workhorse of NLP for years.
But the paper is actually pretty aggressive about why they ditched the LSTM in favor of the transformer. Why was the old way so bad for this?
Well, the name long short-term memory is honestly a bit of false advertising.
How so?
LSTMs are theoretically supposed to remember things over long sequences, but in practice, they are quite restricted to short-range prediction.
Yeah.
Imagine reading a book through a toilet paper tube.
A toilet paper tube.
Yeah. You can only see a few words at a time as you scan the page. If the clue to the mystery you're reading was 3 pages ago, the LSTM has probably already forgotten it because it passed out of its narrow field of vision.
It just drops out of its memory.
Right. And the transformer essentially removes that tube.
It removes the tube and what? Turns on the lights in the whole room.
Exactly.
Yeah.
It uses a mechanism called self-attention. It offers a structured memory. It can look at the entire sequence of text at once and decide dynamically which words are relevant to each other, regardless of how far apart they are on the page.
But wait, the paper specifically mentions masked self-attention. This is the part that always trips people up. If the transformer can see the whole room, why are we masking things? Ideally, shouldn't it see everything to learn better?
Not if you want it to learn how to predict.
Oh, right, the training objective.
Right. Remember, the training game here during the pre-training phase is literally just guess the next word. If I show you a sentence but I let you see the last word, you aren't learning English, grammar, or logic. You're just cheating.
You're just copying the word that's already there.
Exactly.
Okay, so it's like I'm reading a book, but I have my thumb covering the next word, and I have to guess what that word under my thumb is before I move it.
That is perfectly put. The mask is your thumb. The model looks at all the words before the mask. It uses that self-attention mechanism to understand the context, who is speaking, what's the tone, what happened 3 paragraphs ago, and then it makes its guess.
And then you move the thumb.
Move the mask 1 word to the right, and it guesses again. And it does this millions upon millions of times across all 7,000 books.
And because it cannot cheat, it has to actually internalize the rules of the language to get the guess right consistently.
Precisely. You cannot guess the next word in a complicated mystery novel unless you understand the plot. You can't guess the next word in a dialogue unless you understand the grammar and the social dynamics.
The task forces the model to build a deep internal representation of how the world works.
Yes.
Okay, so after this massive pre-training phase, we have a model that has essentially read a whole library. It knows grammar, it knows context, it can predict the next word like an absolute champion.
A very fluent text generator.
But, and this is a big but, it doesn't know how to take a test. It has no idea what a prompt, like summarize this paragraph or is this sentence true or false, actually means. It just wants to write more of the story.
Right. It's just a continuation machine at this point.
Which is a huge hurdle. We have a generic text generator, but the benchmarks require a specific problem solver.
Which leads us directly to the second stage of their framework, the discriminative fine-tuning. the exam phase.
And this is where the paper gets really, really clever, in my opinion. They use something they call input transformations.
Yeah.
Because usually, historically, if you wanted an AI to do a brand new task, you'd have to perform brain surgery on it, right?
Pretty much. That was the standard approach. You'd have a pre-trained model, but then you'd rip out the top layers, add new task-specific modules, change the architecture entirely.
So you'd have a bespoke translation model and a completely separate sentiment analysis model, and they looked structurally different.
Exactly. But these researchers at OpenAI said, no, we want one brain. We are not going to change the model's internal structure for every new task. Instead, we're going to change the input to look like something the model already understands.
They're tricking the model.
They are absolutely tricking it. They are formatting the multiple choice test to look like a continuation of a story, the traversal style approach.
Let's walk through this because the visuals they provide in the paper are really helpful to understand this. Let's take textual entailment.
Okay.
For you listening, textual entailment is basically a logic test. You have a premise, like the cat sat on the mat, and you have a hypothesis, like the cat is on the floor. And the AI has to say, if the premise entails the hypothesis, contradicts it, or is neutral,
Right.
how on earth do you feed a rigid logic test to a model that only knows how to write romance novels?
Well, the model expects a linear sequence of text. So the researchers just stitch the two sentences together into one sequence.
Just jam them together.
Yep. They take the premise, they add a delimiter token, think of it like a special $sign or hard separator, and then they paste the hypothesis right after it.
So to the transformer, it just looks like one long, weird sentence. The cat sat on the mat $sign. The cat is on the floor.
Exactly. And then they just train a very small single linear layer on top to say, when you see this specific sequence pattern, your final output should be classified as entailment or contradiction.
So they aren't building a complex logic module. They're literally just teaching the model that in this very specific genre of story, the ending is always a classification label.
Yes. The model uses the exact same reading comprehension skills it learned from the books. It just outputs a label instead of a new word.
He did something similar for similarity tasks too, right? Where the order of the sentences doesn't matter.
Right. For similarity, since sentence A is like sentence B means the same as sentence B is like sentence A, they process the sequence twice. Text 1, then text 2, and then text 2 followed by text 1. They process both, add the results together, and get a prediction.
It's so hacky, but so elegant. But my absolute favorite example of this input transformation trick is how they handled multiple choice questions.
Oh yeah, the multiple choice is brilliant.
Because a multiple choice question is not a linear sequence at all. You have a question, a context paragraph, and let's say 4 possible answers floating there. How do you feed 4 distinct answers into a single linear input tube?
This is where the traversal style approach really shines. They actually create 4 completely separate sequences.
4 separate inputs.
Right. Sequence 1 is context plus question plus answer A. Sequence 2 is context plus question plus answer B, and so on for C and D.
So they essentially make 4 little parallel universes.
Exactly. They treat each possible answer as its own independent little story. They feed all 4 stories into the pre-trained model and basically ask, hey, which of these 4 stories makes the most linguistic sense? Which one is the most likely to be written?
And the model just scores them.
It scores them based on probability. The story with the correct factual answer will naturally flow better grammatically and logically, so it will have a higher probability score than the story stitched together with the nonsense answers.
That is just incredibly smart. It's like asking the AI, hallucinate 4 different endings to this scene, and we'll just pick the one that you think makes the most sense.
And the most important part of all of this is that it requires minimal changes to the model's actual parameters.
Right. No brain surgery.
No brain surgery. The vast majority of the heavy lifting, the actual knowledge, comes entirely from that pre-training phase on the unpublished books. The fine-tuning phase is just a quick crash course to teach it the format of the exam.
Okay, so we have the theory down. We have the fancy transformer engine replacing the LSTM. We have the thumb over the text pre-training, and we have this clever input sandwich trick for the exams.
The full 2-stage pipeline.
Now comes the moment of truth, the scorecard. When OpenAI actually ran this thing through the gauntlet, did it work?
It worked disturbingly well. They tested it on 12 different standard NLP benchmarks. We're talking everything from sentiment analysis to those strict multiple-choice logic puzzles.
Fair.
It significantly improved upon the state-of-the-art, the SOTA, in 9 out of the 12 tasks.
9 out of 12. And we aren't talking about edging out the competition by a tenth of a percent here. Some of these jumps are massive.
The numbers are actually startling when you look at the historical context. Let's look at common sense reasoning, specifically the story close test.
This is the one where you have to pick the correct ending to a short multi-sentence story, right?
Exactly. The model improved performance on that benchmark by an absolute 8.9%.
8.9%. I mean, in the AI research world, isn't a 1% gain usually enough to get you a keynote speech at a conference?
A 1% gain is a triumph. 8.9% is a paradigm shift. It completely blew the highly specialized handcrafted models out of the water.
The one that really stood out to me when reading the results was race.
Ah, yes, the race data set.
Because RACE is compiled from English exams given to middle and high school students in China.
It's a very tough benchmark.
Yeah, it's not just find the matching word in the text. It requires actual reasoning. It asks questions like, why did the boy feel sad? When the text never explicitly uses the word sad, it just describes a situation where he loses his toy and cries.
Right, it requires inference.
And this model improved on race by 5.7%.
Which is wild. It proved that the model isn't just a stochastic parrot matching keywords. It's understanding the underlying implication of the text.
And it proved that the generalist could beat the specialist.
That was the biggest shockwave. Before this paper, the conventional wisdom was that you needed a specific reasoning bot with complex memory modules to solve reasoning questions.
But this paper proved that a bot that just reads a bunch of amateur fantasy and romance novels is actually better at logical reasoning than the specialized bot.
It dominated across the board. They also tested on the GLUE benchmark, which is a massive suite of diverse tasks. It jumped to 72.8% compared to the previous best of 68.9%.
That's a huge leap.
And it showed incredible consistency, too. It worked beautifully on small data sets like STSB, which only has about 5.7K training examples, all the way up to massive ones like SNLI with around 550K examples. The model just adapted.
Which naturally begs the question, why? Why does predicting the next word in a romance novel make an AI better at answering a science or logic question?
Right.
The paper actually digs into this in the analysis section, and they talk about these zero-shot behaviors.
This is my favorite part of the paper. This is the checking under the hood section. The researchers wanted to know if the model was actually learning these specific skills during the pre-training phase before they even showed it the fine-tuning test.
So, was it learning sentiment analysis while it was reading the books, unprompted?
Exactly. And the answer was yes. They monitored the model's zero-shot performance while it was still in the library phase, and they found that as it read more books, as it went through more pre-training updates, its ability to identify sentiment or judge linguistic acceptability, like in the COEL dataset, it just improved steadily.
Even though nobody explicitly told it to look for sentiment or grammar.
Right. It just emerged.
It reminds me of the Karate Kid. You know, wax on, wax off.
Okay, I see where you're going with this.
Daniel thinks he's just painting a fence and washing a car, right? He thinks he's just doing chores. But he's actually learning the fundamental muscle memory for karate blocks. The model thinks it's just doing a chore, guessing the next word. But to do that well, it has to learn the muscle memory of sentiment and logic.
That is a surprisingly accurate analogy. Think about it linguistically. If I give you the sentence, the movie was boring, predictable, and utterly. And you have to guess the next word.
I can't guess fantastic.
Right. You have to understand the negative sentiment of the preceding list to predict a negative ending. The objective forces the understanding. You can't separate predicting language from understanding language.
They also did some ablation studies to prove this, right? For the listeners who might not be in a lab setting every day, can you briefly explain what an ablation study is?
Sure. An ablation study is basically a rigorous stress test where you remove individual parts of a complex system to see what's actually doing the work.
Okay.
You say, okay, this race car runs really fast, but is it because of the turbocharger or is it the new aerodynamic tires? So you take off the tires, put the old ones back on, and see if the car slows down.
So they started stripping parts off this GPT model to see what actually mattered?
Exactly. And the first thing they did was the most extreme. They removed the entire pre-training phase.
They skipped the library.
They skipped the library. They just tried to train the transformer directly on the specific target tasks, the old way.
And what happened?
Performance cratered. It dropped by 14.8% across the tasks.
14.8%. That's brutal.
It is. But it conclusively proved that reading the library is the most critical part of the system. You can't just skip to the exam. That broad world knowledge from the books, is doing the heavy lifting.
Did they check the engine itself? Like, did they try swapping the transformer back to the old LSTM architecture just to see?
They did. They did a secondary ablation where they swapped the transformer for an LSTM, kept the pre-training, kept everything else exactly the same.
Yeah.
The average score dropped by 5.6 points.
So the transformer really is objectively the superior architecture for transfer learning.
It is.
Yeah.
The ability to handle those long-range dependencies, to see the whole room at once instead of looking through the tube, it's non-negotiable for this to work. The LSTM just cannot hold enough context to become a true generalist.
Wow. So let's zoom out and look at the big picture here.
Let's do it.
We started with this massive bottleneck. We didn't have enough manually labeled data to teach AI about the world.
Right.
So the OpenAI team solved it by building a transformer, letting it read 7,000 unpublished books in a wax-on, wax-off style pre-training phase, and then tricking it into taking standardized tests by making the tests look like story continuations.
That is the perfect summary.
And the result was a single, unified model that completely crushed the state-of-the-art specialized systems.
And more importantly than just beating the benchmarks, it proved a hypothesis that fundamentally changed the AI industry forever.
Which is?
You don't need to explicitly teach an AI what to know. Unsupervised learning is a totally viable path. You just need to teach it how to speak, how to predict, and if you give it enough raw data, it will figure out the what completely on its own.
It really challenges the old way of doing things. Instead of handcrafting a bespoke robot for every single individual task, you build one really smart, incredibly well-read robot, and you just hand it a different instruction manual when you want it to do something new.
Exactly. And that leads to the final, somewhat haunting thought from the conclusion of the paper itself.
Yeah.
They achieved all of this, all these state-of-the-art sweeps, with just 7,000 books, and a model that, by today's massive standards, is incredibly tiny.
Right. 7,000 books is a lifetime of reading for a human, but for a computer cluster, that's just a light afternoon reading session.
Exactly. So the authors leave us with this lingering implication. If the model got this smart, if it learned this much reasoning and sentiment just by predicting the next word on a relatively small data set, what happens when we scale it up?
What happens if we give it the entire internet?
Right. What are the limits of this approach? If we simply feed it more contiguous text, deeper libraries, vastly larger data sets, does the underlying understanding just keep scaling up linearly?
Well, looking at where we are today with models that can pass the bar exam, write production-level code, and generate poetry, I think we know the answer to that question now.
We definitely do.
But it's wild to think it all started right here with a stack of unpublished romance and fantasy novels and a really clever way to guess the next word.
It really was the spark that lit the fire of the generative AI era.
Fascinating stuff. Honestly, I'm going to go read a book right now and see if I accidentally learn karate. Thanks so much for unpacking this deep dive with me.
Always a pleasure. Thanks for having me.
And thank you for listening to this deep dive. If you're wondering what to explore next, think about how much of your own knowledge comes from just observing the world versus being explicitly tested on it. Check back soon for our next deep dive. Until then, keep learning.